Hi, I am Pradosh Kumar, working as an assistant professor in the Department of Biomedical Engineering. In this session, I am going to discuss about Boolean algebra and gates. First, we will see about binary digit. Each of the two digits in the binary system is called a bit. The word bit is a contraction of the words binary digit. In a digital circuit, two different voltage levels are used to represent the bits. Digital 1 is represented by the higher voltage level, which is called logic high or logic 1. Usually digit 0 is represented by the lower voltage level, which is called logic low or logic 0. Logic levels in digital circuits. Positive logic level. The higher value of voltage is considered as logic 1 and lower value of voltage as logic 0, which is called the positive logic level. In negative logic level, the lower value of voltage is considered as logic 1 and higher value of voltage as logic 0. Boolean algebra. It is used to perform the logical operations in digital computer. In digital computer, true represent by 1 and false represent by 0. Logic operations are performed by logical operators. The fundamental logical operators are AND, OR, and NOT. AND operator performs logical multiplication denoted by dot. OR operator, it performs logical addition and denoted by plus. NOT operator, it performs logical negation and denoted by bar. It operates on single variable. Not operation means taking the complement of a value. Commutative law. Commutativity is a widely used mathematical term that refers to the ability to change the order of something without changing the end result. That is x plus y equal to y plus x. Similarly, if you are doing the multiplication operation, that is x dot y equal to y dot x, that is nothing but commutative law. Next one is the associative law. The law states that x plus, inside bracket if you are taking y plus z, then the answer will be x plus y will be in the bracket and plus z will be added to that. That is nothing but associative law. Next is the identity law. In Boolean algebra, there exist identity elements 0 and 1 such that x plus 0 is equal to x. Similarly, x dot 1 also will be equal to x. That is nothing but identity law. Next one is the inverse law. There exists an inverse such that x plus x bar equal to 1. Similarly, x dot x bar equal to 0. That is, we can consider like x plus x bar equal to 1 means if suppose you are taking the value of x as 1 means then x bar will be 0 since it is a complement. So what happened, 1 plus 0 will be added and we will be getting the answer 1. Similarly, if you are multiplying the two terms, that is 1 is the variable, the x means that is you consider that as 1, then the x bar is a complement so that it will be 0. So 1 and 0 multiply means we will be getting the answer as 0. That's why inverse law we are getting that answer. Next one is the idempotent law. This law states that x plus x equal to x. Similarly, x dot x equal to x. Next one is the distributive law. This law states that x plus bracket y dot z equal to, we can combine the bracket into two forms, that is x plus y will be in one bracket multiplied by x plus z will be in another bracket. This is nothing but distributive law. Next one is the absorption law. This law states that x plus x dot y will be equal to x. Similarly, x dot of bracket x plus y, the answer will be x. Elimination law, that is x plus bracket x inverse dot y equal to x plus y, that is the inverse term will be eliminated. Similarly, for the second case also, x dot inside bracket x inverse plus y equal to inverse term will be eliminated and we will be getting the answer as x dot y. Next one is the consensus theorem. X dot y plus x bar dot z plus y dot z will be equal to x dot y plus x bar dot z, that is the value y dot z, that variable will be removed, that is dropped in the answer, because that both the terms are used in the remaining two terms, so that we are removing that term. Involution law. This law states that x bar the whole bar will be equal to x. That is x bar the whole bar to the power bar means value will be the normal value what we are giving. That is x bar will be equal to x. Next is De Morgan's law. This is a very interesting and important law which is useful in designing logic networks. This law states that x plus y the whole bar will be equal to x bar dot y bar. Similarly, x dot y the whole bar will be equal to x bar plus y bar. This is the De Morgan's law. Next, we are going to discuss about the logic gate. A gate is a digital circuit which operates on one or more signals and produce single output. Gates are digital circuits because the input and output signals are denoted by either high, that is 1, or low, that is 0. There are three basic gates. Those are AND gate, OR gate, NOT gate. AND gate is an electronic circuit that gives a high output only if all its inputs are high. AND gate takes two or more in and produce only one output signal. This is a diagram of symbolic diagram of AND gate, where you are giving the two inputs A and B and you are getting the output as the multiplication of two, that is AB. This is a truth table of that. In that we are seeing that for both inputs are 1, we will be getting the output as 1, and for remaining cases the output will be 0. Next one is the OR gate. OR gate is an electronic circuit that gives a high output if one or more of its inputs are high. OR gate also takes two or more inputs and produce one output signal. Here the OR gate, the function is to add both the input and give the output. That is, when you are giving input as A and B, then the output will be A plus B. This is a truth table of that. In this case, If one of the input is 1, that is high, you will be getting the output as high or true. And both the inputs are false, then you will be getting the output as 0. This is a NOT gate. Is an electronic circuit that gives a high output if its input is low. NOT gate takes only one input signal and produce only one output signal. The output of NOT gate is complement of input. It is also called as inverter. That is, for input whatever you are giving, you will be getting the output as a complement of the input. So that this is a truth table which shows that if input is 0, then our output will be opposite of that is 1. Similarly, if you are giving the input as 1, then our output will be 0. NAND gate, which is known as the universal gate because any digital circuit can be implemented with NAND gates alone. So this is a diagram of the NAND gate. That is, for NAND gate, when you are using the output as a bubble, then we will be getting the NAND gate. Here it will be exactly opposite to that of the AND gate. In the truth table, you can see that for all the cases whenever that is like exactly opposite of the AND gate, the output will be opposite of the AND gate. A NAND gate is constructed by connecting a NOT gate at the output terminal of the AND gate. The output of NAND gate is high if at least one of its input is low. The output of NAND gate is low if one of its input is high, if all of its inputs are high. This is a NOR gate. It is constructed by connecting a NOT gate at the output terminal of the NOR gate. The output of NOR gate is high if all of its input are low. Similarly, the output of NOR gate is low if all of its input is high. The logic symbol for NOR gate is shown here, where you can see when two inputs are given A. Next is the XOR gate. XOR gate is a digital logic gate that gives a true output when the number of true input is odd. So it is given as X equal to A XOR B. That is, for an identical input, we can say the output will be low, and for the remaining cases, the output will be high. XNOR gate, which is the opposite of the XOR gate. So whatever we got in the XOR gate output, we have to take a NOT value for that, so that you will be getting the opposite of the XOR gate. That is nothing but the XNOR gate, which is a complement of XOR gate. NOR gate as an inverter gate. Here we are using only the NOR gate, and we are getting the output as an inverted value. That is X we are giving, and through a NOR gate, so that we will be getting the output as X bar, which is equivalent to an inverter. NOR gate as an OR gate. Here we are giving the input, two inputs to a NOR gate, and you are getting one output that will be added, and you are taking a complement, that is a complement of that, so that the output again will be output will be the addition of the two inputs. So again it is similar to the NOR gate working as an OR gate. So this is an example for that. This is an OR gate equivalent of AOI gates, that is AND gate, OR gate, inverter gate. See, if in the top we have shown an AND gate, and the bottom we can see two OR gates or NOR gates are used here, where we are getting two different inputs, and then you are getting the output from the NOR gate, which will be combined with another NOR gate, and you will be getting the output, which will be nothing but the output similar to that of an AND gate. In that case, we are working the NOR gate will be utilized as a for producing the output of AND gate. And next is the OR gate application, which is provided by the NOR gate. Here you are giving an input to the NOR gate, again taking the output from the first input output to the NOR gate, second NOR gate, so that you will be getting the output of an OR gate. Similarly, for inverter case, when you are giving the input directly to the NOR gate, you can get the output as a complement of the input. Hence, it is working as an inverter. This is a NAND gate as an inverter gate. So, when you are giving the input, the output will be the complement of the input. So, the next is a NAND gate as an AND gate. Input we are giving to the NAND gate and output we are getting, and the final result will be uh, there is an AND multiplied value as the output. In this way, NAND gate will work as an AND gate. This is an AND gate, an AND gate as an OR gate. Again, we are giving two different inputs X and Y, and you are getting an output from that, which will be a complement. And then finally, again, once again, you are giving it through a NOT gate, NAND gate, so that you will be getting the output as a summation of the input, that is an OR gate. NAND gate equal to AY gates, AND gate, OR gate, and inverter gate. So, in this way, you can see that NAND and OR gate will work as a universal gates. You can get any type of value gates output from these gates. Hence, these gates are called as universal gates. Thank you for listening to this session. Thank you.